maybe in the meantime, those of you that are in the panelist side where you can write in the chat, why don't you tell us how you're doing? How are things on your end of the world? It's always good to hear from you guys. So maybe just put in the chat, let us know. And those of you that are on the attendee side and can't access the chat, maybe just put on the Q&A. Tell us how you're doing. How are things in your side of the world? Same question for everybody. And don't be too shy. Okay, so I see that Siobhan was on the panelist side, but it's not on this side. It's that's a logistical thing. We can move you over. So if you've given us the forms, we should be able to move you over to the panelist side. If you weren't automatically, put on the chat, maybe either to Andrew or myself, the email that you're using to log into Zoom, which may be different than the email that you're using to log that you put in your application. And so if you in your application use one email and you're using in Zoom a different email, then you wouldn't automatically be moved into the panelist side. So that might be the reason why that happened. I see Brandon is doing well. That's great, Brandon. Jumana is asking if we could talk about some books that are needed. I think Andrew will touch on that. I think he has some recommendations. Anonymous says that there were panelists before, but not right now. Well, we can't help you, Anonymous, because you're anonymous. You need to tell us your name so that we can pick you from the crowd and move you over. Russia is doing great. And they sent the forms twice. Russia, did you send the form for photo release? We can double check that.
And if you did send the form, make sure it was sent to Raul and myself.
Yep. Did you move Publica over as well? Purbita? Or Purbita?
Purbita. I'm trying to check. Yeah, so I guess just the email that was logged in for Purbita is not the one that we have on file. I can move Purbita over now.
I couldn't find Purbita. All right. Well, I'll check some of the, if you're in the panelist and the attendee side, and you should be in the panelist side, just let us know and I'll work through it as Andrew gives his lectures. Okay. Ooh, I see that somebody got their second shot today. Ooh, congrats. That's great. I hope other people are able to get their vaccine shots right now. I know it's scary and not everywhere in the world the shots are being distributed. I'm originally from Venezuela. I don't know if I told you this, but Venezuela has struggled getting vaccines. And so if you're in parts of the world where vaccines are not coming, I totally understand the concern. So, but if you're fortunate enough to get a vaccine, hopefully you're getting vaccinated. Things are relatively fine. I'm quite excited for the session and the practical stuff. That's great, Sid. Yeah, Andrew's has a fun session prepared for today. And I see that Austin is excited to get started. Everybody's not having such a bad day. Meg says that it's rainy in UK. Is that for a change? Because every time in the UK it's raining. All right. Akshita finished the midterms exams. That's great. Good for you. All right. Well, I like to see all your messages, so I'm reading them as I scroll through. I see that. Oh, I see Sohan is having questions about paying for Dropbox. You shouldn't need to pay for Dropbox. We might run into a problem though, for some of you, because you have there is a limited space for Dropbox, and so the more files that get used in the Dropbox folder, the more of your space will be consumed, and so it might require, you might go over the space limit, in which case you would have to pay. If people are encountering this problem, we can try to circumvent this. I think we can come up with clever solutions. Perhaps one clever solution, or one simple solution for this, is for each one of you to create your own Dropbox folder separately and then send us a link. Maybe that's the easiest. Can you think of an alternative, Andrew?
No, not currently. I think that would be pretty simple. A lot of folders to manage, but it's not that bad. I was trying to check if, I don't know if Slack has any cool features that you can do things with. I think it's just chat.
Yeah, maybe in Slack we can do that. Well, that won't work for everybody, but yeah, we can do it. I see some Diego's from Costa Rica. He got his second vaccine today, or 2 days ago. That's awesome. And our friends out in India are a little sleepy, so they're having a cup of coffee. I'm sorry, Asha. Okay, why don't we go ahead and get started? I'll say a couple of boring words, but that are necessary. Let me share my screen, and then Andrew will take over, and he's only going to talk about fun stuff. All right, so you should be able to see my screen. Let me just recap some of the admin stuff that we covered last time, and see if there's any questions about this stuff. So this is a Zoom link. If you're watching this video after the fact, this is the second nuclear physics mentoring video. So if you are seeing this for the first time, then watch the first video and then come back. The videos all can be found on YouTube, in our YouTube channel. You can take a screenshot of this if you want to type out the link. Here's a Zoom link if you want to join our meetings. The meetings are always going to be on Mondays. Our times may change. Next week, Andrew and I are both in vacation. And so that's right, Andrew? We're both on vacation next week.
Actually, Monday I'll be here. It's Tuesday. I can go.
Oh, okay.
Oh, yeah, so we couldn't meet. Yeah, it's the following Monday I'm gone.
Okay, the following Monday I should be back. So I'll be in vacation next Monday, but I could probably join for a little bit. So that might just work out perfectly then.
If not, I can always run it if we want.
Sounds good.
Yeah.
Cool. So one of the things that you need to do is write weekly reports. And what should be a minimum number of weekly reports for you to receive a certification for having been part of this program is 4 weekly reports. So just 4 weeks, not that much work. But if you want to continue working on this stuff, we plan to continue hosting these meetings in the future. And so the reports have to describe what you've learned, what you've done, and what you learn about. And it should include some descriptive text and some meaningful figures. Okay. And I'll give you an example of this because I think we have a really nice one already in our folders. And so the plan is that this is going to be a mixture of lectures and projects. The expectation, some people asked about the expectation for original research. Original research would take at least a year. Okay, so it doesn't mean that many of you can't do original research, but the time scale for that is long. we don't expect most of you to want to continue pursuing this for a year and do a regional research that could then translate into a paper. If a lot of you do want to continue, that's great. In reality, Andrew and I can manage this many mentees through all the way through original research. So what we plan to do is that those of you that carry out these projects and have developed a portfolio that can prove that you have some set of skills, we will connect you with other, or I should say, we will do all the hard work to try to connect you with other nuclear physicists out in the world. They could be in the US, they could be in other countries. And so for us to do that, we need to have a better understanding of your kind of academic background. And so that's what we're going towards. So we decided to use, so we will have weekly meetings, and we will use, for chats, we're going to use Slack. So that has now been decided, and I'll show you the link in just a second. And I should email you this link, and I'll do that after I finish sharing these slides, okay? So the other administrative stuff is that you should have sent us your forms, Annex I and L. I is just to put in the program. L is if you want to be part of the panelists, because as you already know, these sessions are being recorded live. And so if you want to be in the panelist session, we need to get your approval that you're okay with your image being released out in the public. Okay. And most of you have responded, so it's been really great. Here is the Slack chat. So the Slack chat is going to be the same one that we generated for Python for STEM. So if you've already been in the Python for STEM class, then you can use that same chat. And within it, you see there's a couple of different little sub chats. So it's Python for STEM. I have different Slacks. So the Python for STEM Slack, inside of that, there's various different chats, and we created one for the Nuclear Mentor Program. Okay. So you can just go there. I put a little description. What this is for, and you can see that me and Andrew are already there. Okay, so let me put it on the chat for everybody to join, and you can join right away if you like. So here's the link. If you're in Python for STEM, you can just go there directly already. Also, you can find the same link if you send us an email to Python for fit@edu, and you'll get the automatic reply with a bunch of links, including the Slack one. I hear lots of Slack notifications. That's great. So let me close my Slack, because I think I'm going to get bombarded with Slack notifications. So the weekly reports, as we said, we've been putting them inside of Dropbox. You need to create a little folder with your name. Here's my example. Then you have a weekly, each one for each week, and then you have a report. So that's pretty standard. So now let me show you an example of a report that we got that I thought was quite nice. So I don't think that Tuba will mind that I highlight their work. So Tuba Balta, this is the one that they wrote out. There's a lot of descriptive text on what was explained the first week, some descriptive diagrams. These are original. That's great. I value creativity, and if you can write it out, something yourself, that's always great. So plenty of text, quite nice, and then one figure stolen from the slides, also perfectly fine. Okay. And so I think that's all I have to say. I don't really have anything else to say other than I'm happy to answer whatever questions you want. And what I said before is that I said last time, if you haven't taken Python for STEM, today we're going to start looking at programming And so you might want to start by just basically learning the basics of Python for STEM, of Python, which we teach in our class of Python for STEM. The Slack for Python for STEM is the same one that I just share in the chat. So if you, instead of wanting to copy the whole link, and instead you just want to get it directly to your mail, you can just send me an email at pythonforphysics@odu.edu, and you get this automatic reply. All right, I don't think I have anything else to say. So I'm just gonna shut up and let Andrew do his thing. So Andrew's gonna be lecturing today.
Yeah. So you said you'll go through the Q&A to record the missing people from the panelist side.
Yeah, I'll work on that. So if you're on the panel, on the attendee side, I'll start pulling you over. Just make sure to put on the Q&A feature that you should be on the other side.
Okay. So I have some slides that I want to share first to kind of get us in the mode of some of the background tools that we need in order to study nuclear reactions. So I put some material in the Dropbox, and I'll kind of point to it as I'm going through here. But as Raul alluded to last time, our main driving interest in our research is focused on understanding nuclear reactions from the fundamental principles of the standard model, namely from the theory of QCD. To do this, we have to do a lot of things numerical. And even when we do analytic studies, it's often good to make plots or do some kind of toy model calculations, and there's some numerical implementation involved. So you have to be comfortable with some numerical programming language, and many of you are Python, C++, Fortran, even if you like. I know some people roll their eyes at Fortran, but I like the language. So having some comfortable skills with that is important. And another thing within programming is using complex numbers. So complex numbers, let me shrink this thing, it's in my way. So complex numbers are very important in physics, in your, say, undergraduate studies, maybe even high school studies. You've seen complex numbers in one way or the other. And in most subfields of physics, complex numbers are a useful shortcut. So if you think about waves, say on a guitar string here, which you can model by sinusoidal type functions. And when you study wave mechanics and classical mechanics theory, if you have, or you'll get to it at some point, complex numbers are a nice shortcut in order to do a lot of quick algebraic and calculational manipulations. So if the wave here, which I'm denoting as the psi function here, which is a function of x, which you can think is the spatial distance of the string, and t is the time, just regular standard time evolution. And this wave here may be described by some amplitude, which is how high the wave crest goes, some cosine function with some angular frequency, so how fast the wave is waving, which is evolving in time, and some wave number, which is just kind of an equivalent of momentum in this sense for the wave, traveling along in some x direction. Often you'll express this in terms of some complex number. So here the exponential to the I, which I is the usual -1 square root. And you take the real part of this to recover the cosine. But doing this allows you to do a lot of quick calculations, because exponentials, if you've seen these in your studies, and a lot of people have, they're a lot easier to work with than trigonometric functions. So it's kind of a calculational tool in classical mechanics and fluid dynamics and all these other kind of classical subfields, electromagnetism as well. But for quantum mechanics, it's a lot more interesting. In quantum mechanics, complex numbers are fundamental. You need to know them really well in order to describe what we know about nature. So here, now I'm using psi to represent some quantum probability function, which is called an amplitude, which has this same wave-like form. And we use these wave functions to convert to probabilities that we can then interpret in actual data by some operation. In this case, if we have a wave function given by this expression here with some amplitude, some frequency, and some wave vector or momentum vector, as we'll kind of get accustomed to calling it, we can convert this quantum wave function to a probability that we can measure. So it's a real function then, by taking the modulus squared and doing some integration in whatever range of interest. And some kind of example that you may have first seen this is the double slit experiment. When you take modern physics, or when you get to modern physics, you'll be seeing how this works. You have you have some waves propagating, some quantum wave functions propagating from these two holes in this, these two slits, which represent the probability amplitudes of a particle to exist at that space and time. And they can interfere with each other and create very cool patterns. And you learn all about this in quantum physics. We don't have enough time to go through all these details about it, but that's, this is just motivation of why complex numbers are important. And I put some kind of nice papers I found in the Dropbox, one of which is a kind of a technical paper. So if you have some, a good amount of physics background and are interested in some of these ideas in quantum computing, this paper here is an interesting read and arguing why you need complex numbers in order to describe a quantum system. This one's more of a fun one, just illustrating, you can't get away without having some complex nature in your quantum mechanical description. These aren't, I won't say these are required. They're just, for you to take a look at if you feel like. So nothing I'm showing here, I would, say is required to read, just, for your information. For us, the main thing that we're after is the scattering amplitude, which is a type of quantum probability amplitude that describes the probability that helps describe the probability of an interaction to occur. And we convert these scattering amplitudes, which I'm going to denote here as M, to probabilities by doing the same type of manipulation as I illustrated before. We take the modulus of it and square it. And the modulus squared, oh, wrong way, is given by M, the scattering amplitude conjugated. So this is the complex conjugate, which hopefully you've seen in your elementary complex variable study. And this is kind of the algorithm that is used to convert these quantum amplitudes to real probability amplitudes that we can measure. So in this example here, we have two particles coming in. Here I have a kind of a dark gray particle, and here I have a red particle. Some collision happens, and then the particles go out. We're going to describe this thing by the scattering amplitude, M. And this M, this function, is going to be our main object of study throughout these meetings through the nuclear mentor program. This is the thing that we want to get after. This is the thing that experimentalists want to get at as well. Theorists want to calculate these things. It's a central object of our study. This thing here is a function of the energy between the two particles. And here I'll start kind of laying down some notation that we'll be seeing throughout. This energy E here has a special superscript star, which we use to indicate the center of momentum energy. So this is the energy if you have one particle coming in, say, to the right, another particle going into the left. So the momenta are equal and opposite. This is the energy between those two particles as their momenta are equal and opposite. Sometimes this is called the center of mass energy. Colloquially, a lot of people call it that, even though technically relativistic center of mass is different than center of momentum, but it's a minor technical point. But just keep note that this is the energy in a special reference frame where the momenta are back to back. And this is the energy that we can describe the system with. So if it's at low energy, that means the particles are moving rather slowly toward each other. If it's very high energy, like say at the LHC experiment, they're being shot at very, very fast. And this E star is a measurement of the energy between the two particles. An example of one, which you'll be playing with probably next week, is given by this function here. And I'll describe a little bit about the details of this function. So here we have a plot of an M. This is a toy model that I picked out that you can think about. Maybe you calculate from some theory, or you model it with some interaction that you guess is going on in some system, what have you. This is just some given amplitude. It has real and imaginary parts. This is given by the red and the blue. And this is very important to see because it's not like the imaginary part is small or negligible. It's very much, it has different qualitative features than the real parts. And this is just another instance of why complex numbers are important in quantum mechanics. Because the imaginary part contains actual information about the process. In the x-axis, I plot the center of momentum energy divided by the mass of the particle. That way, the x-axis is in dimensionless units, so I can just keep things kind of nice and tidy. I don't need to specify what the energy is in, say, mega electron volts or what have you. The equivalent way of thinking about this is I'm choosing the mass of the constituent particles to be unity. However you want to think about it, the point here is this point here at 2 is a very special point. It's what we call the threshold energy, and I'm denoting this by E star TH. And this is equal to the minimum physical energy that the two particles can have in order for some interaction to occur. And this minimum energy is just the two particles. Here, they're both equal mass particles. So, say 2 protons. They're just sitting there. There's no motion. You see, there's no momentum variable. It's just twice the mass of the particle. And this is the minimum energy. It's called the threshold energy. As we increase the momentum, the center of momentum energy will increase, and this number will become greater than 2m. And so you see here, this is the minimum energy. And as the energy increases, we move off to the right. Now I have plotted the amplitude below 2 to illustrate that this amplitude does have an interesting feature in that the amplitude at any threshold has this cusp-like feature. So you see this right here, the imaginary part is 0, which we'll get to more of that details next week of general features of the scattering amplitude. And then at threshold, the imaginary part turns on, and this real part here gains a little cuspy guy you may see right here. This is a general feature of scattering amplitudes. So I'm just pointing this out now. You don't need to fully understand why. We'll go into more details why this is as the weeks go on. But this quantum scattering amplitude is not what's measured in experiment. What's measured is something proportional to the probability of that interaction to happen, and that probability is proportional to the modulus of m squared. So here on the bottom right, I plot the modulus of m. I multiply it by this kinematic factor rho called a phase space, which again, we'll get to next week, but just know I don't want to cheat you here. There's an additional factor here multiplying it. That factor is just to normalize this to 1. It's easy when you have things normalized to 1 because then things fit on the plot and you can check how things work. We'll again get to that next week, but this quantity here is still proportional to the probability. Or actually, if I take this thing and square it, it'd be proportional to the probability. This kinematic function is just making my life easy. And you see here that below the threshold, this thing is 0. So if the energy below the 2 particle threshold, or if the energy that you're kind of pumping into your system is below the energy that the 2 particles can be created, then you're not going to get any interaction. So this is showing that there's 0 probability of that reaction happening, which makes sense with what we would think. As the energy turns on and increases, the probability shoots up. It goes its highest around here, and then it starts going back down. This point here is not a universal, but it's an indication of a resonant system, which means that as the energy gets closer to the system, the two particles are more strongly interacting, and they're forming this quasi state that's living for a very short time before it decays away. And it's peaking around this region because this is roughly where the mass of this quasi particle is being made. Excuse me. You'll see more of these features in the weeks to come as we start exploring these things in detail. An example from real life data, I took this from the particle data group. This is an example of Pion Nucleon scattering. So here we have in blue a pi plus meson interacting with a proton, and in red we have a pi minus meson interacting with a proton. And you see kind of these general features as the energy. So this bottom axis is the center of momentum energy. This axis here is the momentum of the beam as it's hitting the particle target. You don't need to know, all the details about this, but you see the general feature. This y-axis is the cross section, which is proportional to this probability I'm talking about, this absolute value of m squared. And you generally see these types of behaviors, and experimentalists will measure such things, and then they want to analyze them, or maybe theorists want to analyze these and kind of see the physical content. And there's ways to convert these types of measurements into scattering amplitudes. And so we can go from taking the scattering amplitude from some theoretical prediction and calculating what the cross-section or probability is. And we can go the reverse of taking data and interpreting what the scattering amplitude will look like. So this is taking a piece of this data here, and I don't want to describe all these details, but this is some analysis where they infer what the real and the imaginary parts based upon this cross-section. And there's a lot of useful and important features of scattering amplitudes that allow you to do such an analysis. And we will explore those starting next week. But many of those features rely on complex numbers and using properties of complex variables. Some reference. Yeah.
Andrew, maybe just to stop you. So you have a question on the chat?
Okay.
But also maybe since these are panelists now, they can also ask their questions in themselves. So maybe what you can do for the panelists, what you can do is raise your hand feature. You can press a little button like I'm doing right now, and then wait for Andrew to see it or for me to call it out. So I think, Miguel, if you're comfortable, you can ask your question in yourself.
Yeah, sure. I was asking if the resonance lifetime is related to the peak intensity in the diagram.
So the resonance, hello, Miguel. Nice to hear your voice. So that's a good question. In general, when you have an isolated resonance, and I'm trying to be careful with my words because I'm very picky when people say this wrong, but for a system like this, the qualitative idea is that the location of this peak is related to the mass of the resonance, so how heavy the thing is. The width of this peak at half, the full width at half the maximum is related to the decay width of the resonance, and the decay width is related to the inverse of the lifetime. So the peak location is roughly where the mass of the particle is. And if you take this width around here and invert it and convert the units to, say, seconds if you want, that will give you the lifetime of the resonance, of how long it lives. I say qualitatively because we have a more rigorous definition of resonances, which holds for any case here. Because the location of the peak may not exactly be the mass. Only in very special situations does that actually occur.
Okay.
Sorry?
No, okay. I get it.
Okay.
And a quick question will be, if a system doesn't have an isolated resonance, how should the graph look like?
Let me show you an example momentarily. Okay. Let me get out of this. And so while I'm digging that up, I think Ahmed had a question.
Yeah, I had a question.
Mhm.
What could you explain again? What is the center of momentum?
Yeah. So let me go back to here for a second. I'll have to. So the
I mean,
center.
where is it located exactly?
So the center of momentum. And you know what? This is why I brought this up. Okay. So hopefully you can see my a white screen. This is my tablet.
Yeah, we can see it.
Okay. So if I have two particles here, it's called particle 1 and particle 2. This is, oh, let me do it like this first. Particle 1, particle 2, and they're moving. This one has momentum P1. This has momentum P2. If I transform to a reference frame, and by transform, I mean in the relativistic sense, if you had special relativity, the Lorentz transformations, but I'm just going to put myself in a frame where the total momentum, which is P1 plus P2, is equal to 0. So this means P1 is equal to minus P2, and I'm going to define this thing as P without a subscript and a star. That star is indicating that I'm in the center of momentum frame, which is a frame where the total momentum is 0. So this means particle 1, we have a momentum going like this. Particle 2, we have a momentum going like this. And this is just a special frame that's convenient to analyze binary reactions because the particles are going back to back. Does this answer your question?
Yeah, thanks.
You're welcome. Let me stop sharing real quick to bring up a nice example of
maybe while Andrew does that, we should have moved everybody that sent us their forms from the attendee side to the panelist side. If you're still on the panelist on the attendee side and you've sent us your both forms, then let us know. Okay.
So here, I'm showing some plots, some of which Dr. Briseno has performed these analyses from some lattice QCD calculations of some scattering amplitudes. I won't go into detail about all these different reactions, but you see kind of what type of particles are involved. And in this case here, this is not an isolated resonance. There are resonances. Here there are two resonances kind of interfering with each other, one called the sigma, one called the F naught. And you see this behavior is far from that simple, let me go to here, this simple kind of peak-like behavior. It's much more complicated. And even for this guy here, this A resonance, because of its location, it has much different behavior than this general peaking behavior. So this is why I said qualitatively, because if you have a nice resonance, like in this case, you can make those statements and be qualitatively okay. But in general, there's a much more rigorous definition, which we'll get to in the weeks to come to describe what a resonance is.
Okay, thanks.
You're welcome. I don't see any more questions, but if so, yeah, please raise your hand. I'll try to stop. Oh, Jumana has his hand raised, or her hand raised. Jumana? No. Okay. So let me continue then. Back to some references which may be useful. So it's hard to pinpoint great references in my opinion, but I'll point out some ones that I rather like, two of which are quantum mechanics books. If you are at an undergraduate level and you want in my opinion, a nice intro book on quantum mechanics, this book by Townsend is really good. It has a lot of, I think, good discussions on the way I think about quantum mechanics, at least. And it has some chapters on scattering theory, which are useful to scan. The book here by Sakurai and Napolitano is a graduate level version that has a very similar style to this one, which I like it a lot. Again, it also has a chapter on scattering theory, which is useful. Both of these perspectives are for non-relativistic quantum mechanics. We do relativistic physics, but the ideas are very similar. So don't get bogged down by the fact that it's non-relativistic for relative or relativistic. The ideas, a lot of the ideas hold over. We just have to fix, correct for the relativity point of views. That being said, I don't like suggesting people to buy books unless they're very serious about looking into it and reading it. There's other great quantum books that exist. Any good quantum book has chapters on scattering theory and angular momentum and things that I find important in general quantum mechanics. So, that's my warning. I'm not trying to suggest you buy these things for these discussions. I just find these books helpful. Other quantum books work. There's another book that is based entirely on scattering theory by John Taylor, who wrote a very nice book, again, covering non-relativistic scattering theory. But again, a lot of the ideas hold true for relativistic physics as well, with minor corrections. This is a Dover book, so it's rather inexpensive. Again, it's not mandatory, but if you're interested in general scattering theory, you find this research fascinating. I like this reference a lot for your first introduction to scattering theory. And finally, the Joint Physics Analysis Center hosted a couple of summer schools a while back on scattering theory for hadron spectroscopy, which is the fields that Raul and I study, which I'll show you an example here. If you go to this website here, you'll be taken to the International Summer Schools of Reaction Theory 2015 and 2017 edition. Here you'll see some links to 2017 lectures, 2017 seminars, 2015 seminars, and some references. So there are a lot of references here. A lot of these are aimed at graduate students and postdocs. So don't be don't be dissuaded by this, that a lot of this material may be over your head. This is for more working professionals, but some of the info in here may be useful if you decide to continue on your journey to studying this type of physics. In particular, the 2017 lectures, Team 1 and Team 2, which I had the privilege of giving some lectures during this section here. If you click on those links in the 2017, you'll find some video lectures, some notes, some exercises. Not all of this material we'll be able to get through in our discussions in this program, but if you are serious about studying scattering theory, especially for spectroscopy, all this material has to be understood at some point in time. So if you decide to, say, go to graduate school or you're in graduate school for this type of stuff, I give this a check out. The most interesting stuff, I think, pertaining to this discussion today is lecture material on complex analysis and some by Adam Szczepaniak. There's a lot of material in here that's maybe not important right away, but the first, say, third is kind of interesting to look at. And the first third is what I cover in the Python notebook I have prepped for you guys. Okay, so let's take a look for So we have some questions. Probit asks, would Peskin and Schroeder be overkill for this project? No, Peskin and Schroeder is a quantum field theory book that some people like, including, I think, Dr. Briseno. I think it's a fine intro level quantum field theory book that has a lot of nice information in it. I don't really use it too much. It's not my personal favorite, but again, there's many books that exist. That one I think is a fine one to be looking at for some general features of scattering theory, and also just quantum field theory in general. So yeah, if you find that book useful, please, take a look at it. A lot of this, a lot of the introductory material they give does hold over to the things we discuss. Jumana, you have your hand raised.
Yes, sir. I am referring to the Griner's books currently for my other subjects, including quantum mechanics and electrodynamics. Would it be okay if I use the same author for the scattering theory?
Yeah. So if you have books you like, so first of all, hello, nice to talk to you. If you have books you like, the ones I'm referring to are my personal go-to references. That does not mean they need to be yours. The Griner books are nice introductory examples. If I had to list every book I look at, the slides would be filled with nothing but books I look at. So the books I'm recommending are just some simple recommendations. Griner books are okay. Other field theory books, quantum books, whatever you're using for self-reference, if it's a published book, should have some info on the topics we cover in some form. And don't get bogged down too much about trying to understand all those details. We'll try to give you as much info as we can from our side, so you're not lost, I would say. But yeah, the Griner books are perfectly fine books.
And sir, we will be using Python programming language over here. So for that, which reference books would you recommend?
So for programming reference books, so I'm not, so I do some coding in Python, but it's not my go-to language. My go-to language is C++. But for Python, I found most of the help I need just through Google searches on website like, just like Python. So Python has a great tutorial help web page. I think Geeks for Geeks is another kind of website that talks about all that stuff. Those references I think are sufficient. If there are any specific ones that people like, maybe they want to drop them in the chat so people can see. I don't have any particular ones that I go with. I don't know if Raul, you have any books on Python you like, but I imagine it's a lot of just web searching for help.
Yep.
Yeah.
I don't know if I have any books to recommend.
Okay. Yeah, I see there's one in the chat by Risha. Yeah, that's probably good. Yeah, so sorry I can't be more helpful there. For programming language, a lot of times it's just web help. Stack Overflow will be your best friend if you do a lot of programming. Aditya?
And so,
Yeah.
oh, sorry.
No, go on, please.
Okay. I'm actually a bit confused whether we'll be dealing with the Python programming or the theoretical aspect of the nuclear physics.
Can you say that again? I couldn't quite hear your comment.
I asked whether we will be dealing with programming in our mentorship program, or we will be dealing with the theoretical aspect of the nuclear physics that you just explained, scattering amplitude and such.
I see, yes. You'll be dealing with both. We'll have some kind of suggested exercises and kind of opportunities to do some analytic theoretical work, and also some computational programming. And at the last part of this, I'll show a Python notebook, which you can use to kind of get familiar with performing some complex, and by complex, I mean complex variable manipulations.
And sir, a small request. Could you upload whichever of this school, summer school PDFs, if you have any already downloaded, which would be easier for us.
Okay.
I'm
So
sorry if it's too much.
No. So I put these notes that I'm presenting today in the Dropbox. I can download the specific ones from this JPAC website and put them on mine too for your convenience.
Thank you so much, sir.
Aditya, if I pronounced that incorrectly, I apologize. Would we imagine the real part of the scattering amplitude versus energy to represent some physical observation and the imagined part to be more quantitative property? No. If I go back, it is both the real and the imaginary parts are required in order to have this physical observation. If you had, so you can imagine this would be what you physically observed. If you only had one or the other, you would not get this full feature. You would get only a piece of it. So the real and imaginary parts are both vital to understanding scattering processes. What is not clear up front is how can I have, say, a single line here representing kind of one function. This has information from, say, two separate functions, the real and the imaginary part. Given this, how can I understand two separate functions given one function? And the way we do that is using something called unitarity, which is related to probability conservation, which links the real part and the imaginary part, so they're not completely independent. This does not mean that the real and imaginary parts are that only one is needed, because in general you can have multiple scattering processes in which you have more than, say, one function to look at. But we can link the real and imaginary parts into one real function, which can describe both of these parts simultaneously. So it's there are ways using physics to link these ideas together in a bit more systematic way. And we'll start dealing with that again next week. But just note that the real imaginary parts are both needed to reconstruct the full probability interpretation. Trying to get through. So someone is asking if they haven't started their undergraduate classes yet, how can you make sure to have the theoretical background to keep up with the project? So I think the idea behind Dr. Briseno and I in doing this is not to enforce upon, say, rigorous exercises that you must follow in order to complete this. We're trying to make this accessible for any level, including those who are just starting out. Our main goal for you is to take away something from this program. It may just be some qualitative understandings about our research. Maybe you want to go through the Python for STEM courses to learn a little bit about Python if you're not familiar with programming. Maybe you'll just hear a bunch of the stuff we're saying and try to follow along as best you can in order to understand the physics we do. I would say that should be your goal at the level that you are, to try to take away as much as you can. Don't get too worried about not following every single step or derivation or plot we make. Try to understand the qualitative features of this topic and the research we do. And that way you can, in these weekly reports we're asking, that's what you should focus on giving us. If you are more advanced, then maybe you'd expect to do a bit more and want to kind of test your own limit of knowledge. So I would say don't try to stress out about that. Try to take something away and use these opportunities to learn and ask questions. Okay. So let me Yeah. So I have on these last slides just some basic useful information for complex numbers. If you haven't seen it, I won't go through all these in detail. This is not going to be a complex analysis lecture. This is just to remind you of some basic notation and kind of symbols we may use. If we have a complex number, which I'll call Z, which is given by x plus iy, where x and y are real numbers, and I is the square root of -1. This is what makes us go into this complex domain. This Z here is a complex number. There's operations that are important, like taking the complex conjugate, which we denote by this little star here, which flips the sign of the I, of the complex I. And if you take the complex conjugate twice, you get back the number you started with. The real and imaginary parts of the number are given by x and y respectively. So x is the real part of the complex number z, y is the imaginary part of the complex number z, and you can calculate this based on z by taking various linear combinations of z and z star. Some other important quantities is the magnitude of a complex number, which is given by essentially the Euclidean norm, if you know from, say, Pythagoras, the square root of x squared plus y squared. It's a positive definite number. This is also given as the square root of z times z star. Some various algebraic properties you should be familiar with. We often represent complex numbers in their polar representation. So z is given by r, which is the radius of, or the radial part of the complex number, which is r is simply just the magnitude of the complex number, times an exponential to the I phi, where phi is a phase, which this phase here is the origin of a lot of subtle issues in complex variable study. But here I'm just starting off by taking the phase between minus pi and pi exclusive inclusive. And the phase here can be computed from z as the argument of z, which is defined as this various cases of the arctangent function. And as a shorthand, in numerical applications, there is a function that builds in a lot of these ideas. It's of the arctangent for these different cases. It's called ATAN2. Python, C++, and Fortran have an ATAN2 function. I urge you just to Google it and read about this ATAN2 function for the language of your choice. It builds in the domain specifics that the arctan function doesn't build in itself. Okay. As an example, and then we'll go to my notebook momentarily. In Python, for complex numbers, you need to import the CMath library if you're dealing with pure complex numbers. At some point, you may be dealing with arrays, and the NumPy library has its own built-in complex number library with it. So just keep that in mind, that depending on if you're working with arrays or not, you may need to import or use slightly different functions. But here it's just dealing with simple numbers itself. You can make a complex number from real and imaginary parts. So x is 5, y is 3, by defining z is equal to complex of x and y, which converts the x and y separately into a complex number z. And then if you print the real and imaginary part, if you take this code and paste it into your Python script, you should get out 5 and 3 separately. In C++, here the example I have here is C++. You need to import the complex standard library routines, and then you can define a complex function in a very similar way. Std complex double of my complex is what the variable is named here, of 5 and 3, and then you get a complex function that is 5 plus 3i. So if you haven't used complex numbers at all in any programming, these are the general things you know for Python and C++. If you do Fortran, it's a lot easier than that. I didn't give an example because not many people use Fortran, but there you go. Other languages have it their own way. If you're using a different language, you'll have to go into that. These are the languages I'm most familiar with. So some simple exercise for you guys to make sure you know what you're doing. If this is your first time with complex numbers, I recommend, again, this is not mandatory, but recommend you give these exercises a try. Take some time to read a little bit about complex numbers and test finding these various quantities I ask you, and also to numerically implement finding these things with the language of your choice. If you're very versed with complex numbers, these should be a very simple exercise for you. And on that, I want to move towards my Python notebook. But before I do, maybe I see if there's any questions. Okay. Esha asks, why did we use n equals instead of something like print x for the Python code? Let me take a look at what I have here. So as in many programming languages, you can do things in a variety of different ways. Here, the end here is signifying that it's doing a I forget what the word is, but when you do these prints and you have these extra arguments, it's formatting. It's formatting the print to look a certain way. So you don't need to necessarily do this. You could have just had print, the real part, blah, 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 is comma, then z.real in the same line. Here, it was just given in two separate lines. This is totally random and arbitrary chosen. And I think I took, yeah, I think it may be just a line break. I took this example from somewhere and I haven't run it in a while, so I don't remember exactly what it does. Give it a try and see what you get. I don't know if it's a line break or not, but I don't remember anymore. But yeah, there's many ways to do it, so don't worry too much about specifics of how this has to look. Code it in a way that is legible for you, has comments to help you understand what you're coding, and helps anyone who's looking at your code understand what you're coding. Yes, it is a line break. I'm being confirmed. Okay, thank you. Okay. Septarshi in the Q&A asks, how do I unmute myself to ask a question? Should I raise a hand first? You could raise a hand, would be appreciated. There should be a mute button on the far left if you're a panelist. If you're not a panelist, then you cannot do that. So you'd have to send in the forms in order to be promoted to panelist. All right. So let me go to my notebook real quick. So I put this notebook in the Dropbox as well. It's a Python notebook. I'm using VS Code, Visual Studio Code, in order to run my Python notebooks. You may run it however you'd like. I use the Anaconda suite in order to compile and run my Python scripts. I believe this is the suite that is recommended in the Python for STEM to get all that up and running. So please visit the Python for STEM for some more information on that. Use the Slack channel to ask for help and try to get this installed or to get the relevant link installed. I put some more references on complex analysis here, which may be useful for people who are working on this. But in general, the way this is structured, so I first have, so I first have a block here, which is importing, that kernel wasn't started. Let me start this kernel. Okay. So I first have a block here that just imports a bunch of tools that are needed in order to understand, to make the various plots and everything I need. A little bit of description of what the codes are doing. So here, this first block is just looking at analytic functions. So analytic functions are complex functions which have continuous derivatives everywhere inside some domain. So an example I give here is some polynomial of order 2. And here, I'm choosing just some random numbers A, B, and C, defining my function. And I made a simple plot function. And here I'm going to run it. the random numbers it chosen was 4.6, 0.35, and 3.78. And it gives a plot of this function, both the real and the imaginary part. So here the real part is given by the solid line, the imaginary part is given by the dashed line. We then plot this function in a few different ways. So this is a simple linear plot. And I recommend these different ways of playing with this notebook so you understand different visualizations for looking at complex numbers or complex functions, because looking at complex functions for our scattering amplitude are going to become very useful to do, looking at the real and imaginary parts. It's also useful to compare at different for different types of functions. So here, this was plotted for z is equal to x between -3 and 3 plus I times 0. So the imaginary part of the argument is 0. In this plot here, I compared different versions where you have the real part of f of x plus I, the real part of f of x, and the real part of f of x minus I. So you can see the differences when you plot the functions at various locations. We have a couple different other plotting utils for complex numbers. One is domain coloring, which gives some nice visualization of the phase of the complex number in terms of these colorings here. Sometimes these are not as useful, and then I'll move to this, what I call Argon Plot 2D, which plots the real and the imaginary parts in the X and Y plane separately. For excuse me 1 second, my computer is going to die. So let me get my charger real quick.
In the meantime, I think everybody has been officially moved to the panelist side. If you were on the attendee side, let me know if there's any final stragglers. And all the notes are available on the Dropbox folder, which is the comments folder that I've sent everybody, not the ones that you personally generate. So within the groups folder, there's ones that are labeled by my name and Andrew's names. Under Andrew's, you should be able to find these, all the content that he's sharing today.
Yeah. So for instance, just in the Dropbox in the Andrew Jakura, I have this had spec x0 complex to I pi y NB. This is this Python notebook I'm sharing. So forgive me for going a little bit quick, but my purpose of this notebook here is for you guys to experiment with this and check it out. I don't want to go through every single detail. I want you guys to explore it and give it a try. Another type of function here is the Argon Plot 3D, which plots these same two functions here, but in a three-dimensional way. So here, take a moment. Here, the x and y axis are the same as above, but the z axis is the result of the real part and the imaginary part of the function. Note here, all this time it's been for analytic functions. Analytic functions have kind of a smooth behavior inside the domain of interest. There are examples of non-analytic functions, and there are kind of two examples we want to worry about. One is functions that have pole singularities. So these are functions like 1 over z minus z naught, and this is an example here. So this f of z here is some numerator divided by z minus z naught. So this is a typical pole-like function where you've seen, so like 1 over x has an asymptote at x equals 0, where the function blows up at infinity. And this is a very characteristic of a pole singularity. And here's more doing the same exercises as above, but for a pole-like function. And here's just an example of this pole function here, where you see this asymptote happen at this pole location I chose. I'll skip this and let you explore to go to the other type of singularity we're interested in, and that's multi-valued functions that have branch cuts. So the square root function, let me go to my notebook real quick. So the square root function, f of z equals square root of z, if you think about looking in the complex plane, if for real numbers, when z is less than 0, the square root does not exist, right? So this is the whole origin of how complex numbers start. And the characteristic features of this is that the square root function has a value on this side. So if we have, let me draw this thing here. So for negative numbers, the square root function does not exist. So if we go infinitesimally close to this real axis from above or from below, we can get a number, but not on the real axis itself. This point here, where the square root function ceases to exist for real numbers, is called a branch point. And the line in which the branch, in which the function doesn't have any real values, is called the branch cut. So this here is a cut. So this square root function will have a value here and a value here, but not on the line itself. What's more interesting is that the value above the cut and the value below the cut need not or are not the same. And that is what this Python exercise is showing here. So it's showing for the square root function here, plotting the real and the imaginary parts. You see the branch point at 0, and then the function is discontinuous about that negative x-axis. The branch point is fixed for functions like the square root function. However, you can rotate the branch cut if you feel like it. So here's a 2D plot. You see clearly the function's different from below and above. Here's this example of plotting the phase and looking at how the phase changes as a function, or how the square root function changes as a function of phase, and there's a discontinuity as you cross this cut here. You can change the location of the cut, which is what we want to do in scattering physics. We'll get to that next week, but here I do a simple example of a square root where you choose the location of where you want the branch cut to be, and here I chose it to go along the positive x-axis. And this is the situation we're going to want for scattering physics. So here you see the branch cut come to the right. So so there's some questions. I see Rahul just raised his hand. Rahul, do you want to ask your question?
Yeah, thanks. I was just wondering, what exactly are we referring to when we say a branch? Because when we talk about, a space, you think about axes or like a line or plane. So what exactly is the branch?
Mm-hmm. So square root function is a multi-valued function. As you need to, so the idea here is that you would need to go around twice in order to get back at the starting point you have. So let me go back to my picture here. Let's do the example. Oh. So here, I'll draw the cut this way, just so I can do this. So here we have our branch point and the cut exists here. So here I would evaluate my function, say f of z, let's say plus I epsilon. So it's slightly above the real axis. Here I would plot it f of z minus I epsilon. And the function is discontinuous here. What the branch means, it's just a technical term that we've chosen to describe the complex. So this is, let's say, the z plane. So this would be the real and the imaginary parts. As the multi-valued function branches off into different solutions. So here, if you were to evaluate your function, let's say you get +1, as you go around, you would get, say, -1. For the square root function, you need to go around twice to get back where you were before. And that this branch is indicating that there is kind of a copy of this sheet, I'll call it, which it's just hard to draw. So if you imagine you're up here, you start going around, and then you can move on to a different sheet, which is just a different branch. You're gonna get branches on a tree, and you can go around again to come back where you once started. So the square root function is a two-sheeted object. You have to go around twice before you come back. And that is this whole idea behind what branches mean, is that the function has multiple values and you're branching off to either the kind of primary or principal branch, or you can go around and have to do multiple revolutions before you come back.
Right, got you, thanks.
Mm-hmm. This is not, say, the easiest of topics to get at. And while I would say your goal is not to understand these features 100% during this, we want you to start getting familiarized with the ideas so you can work with basic complex functions, because our scattering amplitudes are going to have these square root cuts in them. So we need to be aware of it. We won't do too much with these, but we just want you to be aware of it. So this notebook you have, it is for you to play with and understand and try to get to get at some general features of plotting complex functions. You don't need to go through all of these little exercises in here, but try to go through a little bit of it to get comfortable with the ideas. I see a hand raised by Jumana.
Sir, can you explain the branch, the concept of branch in Python, means the diagrams in Python, the 3D plots in Python?
Can you repeat that, please? It's a little hard to hear.
Sorry, sir. I am saying that, can you explain the concept of branch using the graphs, the 3D plots of Python?
Yeah, so here, yeah, so if you imagine here that this is, like this is the complex z-plane of our square root function. There is a point here where the square root function does not have a unique value anymore. And that point here for the simple square root is 0. For the location that most mathematicians choose square root functions, we choose the branch cut to be going to the left, meaning this is the location where we start dividing up our principal branch, which is just the main branch of the function, where you would have a unique value. So this function has a unique value from the just before you get to the branch to just above you get to the branch. If you want to go to other branches, you need to continue this function underneath this branch or above this branch, and it connects in a very weird way. I think I have something built up I found online that I like. So here's an example here. For the square root function, you have to go around twice to get back to where you were. This here is the branch point. So this is the point I was showing. And you see here, this branch point here has this branch cut here to where the sheet, to where the square root function becomes multi-valued. this is the exact same situation as here. This function is becoming multi-valued. We're defining this branch cut so we can have a unique value function. To get the other values, you would just need to go around a second time, going through this cut and back around. This is what this dotted line is showing here. So it's a little hard to see on here because I've only plotted the principal sheet or the principal branch. But the square root function has these types of behaviors, and I would recommend checking out this blog reference here on branch cuts with square roots for a little bit more detail, which I've taken some of these examples. Kind of like a Mobius strip. Yes, in the way that, in a way, yes, depending on what you mean by the Mobius strip, in that you are unraveling this complicated multi-valued sheet structure into one single street that you can continuously go on, then yes, if that's indeed what you mean. But right now, I think just to think about this as some, it's the same square root function. We're just giving meaning to what this thing means when we reach locations that are not the ones we define with real numbers. So we've gone for a little while now. Are there any questions? I apologize if I didn't go into full detail if you have no experience with complex analysis. The goal here is just to play around with these notebooks. If this was too much for you, I would say start simpler, look at the Python for STEM course and just read about basic complex numbers. But if we want to continue with any scattering type analyses, understanding how to plot complex functions is important. So here are some utilities in Python. If you use C++, you can use GNU plot to make plots, or maybe Python if you want to make plots, and to be aware of functions like the square root, which are multi-valued functions. So we're kind of purposely not giving you all the details you need because we're trying to have this exploratory research idea. So use this opportunity to learn the simple ideas, connect with your colleagues, and ask questions. So maybe this is a good place to stop for today. If there's any other questions or comments, or any comments from admin side. If you haven't been promoted, just make sure we have the emails that we are registered, that you are signing up for with the Zoom link, so we can promote you permanently, and make sure the forms are sent to Raul and myself.
I think most of the ones that were still, I think Diego was the only one that I hadn't promoted. But I think otherwise, I think we got everybody.
Okay.
Regarding the question about when do you have to post your reports, there's no, I would recommend to do it the week of, but if you do it after the fact, that's perfectly fine.
Yeah, I think I don't want to speak 100% for Raul, but we want to have this as a more educational experience, not some rigorous have to get it done by midnight or something like that. This is for you to learn and ask questions and experience what we do.
Yep.
Esha's asking, will we have a Thursday meeting this week?
Yes, we will.
Okay.
Yeah, last week there was a little bit of miscommunication within the REYES team. So this week we will have a meeting. I think we agreed at noon EDT. So that's Virginia time. So we will have a meeting, and it's going to be more casual. It's not going to be lecturing. It's just going to be everybody, you and the other mentees, just talking and getting to know each other.
Mm-hmm. I see Venkat has a question.
Yeah, hello. So you showed a slide in the beginning of real and imaginary plots, right? Like the starting of scattering amplitude for Pion Nucleon decay, scattering, sorry.
Are you referring to this thing here?
Yeah, the very something before that, couple of slides. So there you measured the momentum in the lab frame rather than the center of momentum frame. Is that some sort of convenience in data collecting or something, or is there a reason behind it?
Yeah, so here everything I'm giving is the center of momentum frame. Here, what was measured in these experiments is the momentum of the pion hitting a stationary target proton. So the measurements were done in the P lab, but you can convert this. It's some simple kinematic conversion, not necessary for today to understand, but you can convert this to E.
It's just based on convenience, right?
Yeah, you know, so some experimentalists may like looking at P lab, some theorists may like looking at E star, vice versa. It's kind of just a convenient choice. Here I plotted both.
Okay, thanks.
Mm-hmm. There is a question. Abhishek, I apologize if it's mispronounced. Does branching happen even in singularities like exponential z, which has a singularity at 0? So the exponential function does not have a singularity. The exponential is an analytic function. It's the most analytic function. It's called an entire function. So if you look, I'll go to this real quick. My poor drawing here. So the exponential function at x equals 0, e of 0 is just 1. So this thing does not have a branching point at 0. It's a well-defined function at 0. Moreover, at any value of x, or if we go to the complex realm, e of z, this is analytic everywhere except when z approaches positive or minus infinity. So this is a special singularity called an essential singularity. But other than this, which all polynomials have an essential singularity as z goes to infinity, but there's no other singularity of the exponential function. And indeed, the logarithm, as some people point out in the chat, is an example of a function that has a singularity. So the log of z equals 0 goes to minus infinity. So this thing is blowing up at z equals 0. So the log function itself has a branch point at 0, and mathematically we usually set that thing going to the left. So this is very similar to the square root. The square root function and the logarithm both have these singularities. And more complicated functions like cube roots or quartic roots have these as well. The ones we're mostly worried about is the square root function and the logarithm, but square root function primarily. You meant the exponential of 1 over z. Yeah, so for 1 over z, yeah, then for the exponential of 1 over z, this thing has the singularity then, because as c goes to 0, the exponential explodes. So that is where the singularity, the branch, it doesn't branch though. It's just it's a It's not essential singularity. There's another name for the singularity, and I can't think of what it is. But yeah, at z equals 0, this function does have a singularity that exists. So the main singularities we're interested in are pole singularities. So this is where 1 over z minus z naught. If we have, say, in the z plane, this is e naught, then this function has a pole at that location. So if we look as an example, 1 over x to plot it in the 2D line x. Sorry, wait. This. There's an asymptote at x equals 0. So there's pole singularities, and then there's the branching singularities for multi-valued functions like the logarithm or the square root. All right. Sid has their hand raised. Sid.
Yeah. Hello.
Hey.
Hello.
Hey.
Yeah. So, could you go back to the scattering amplitude plots, please?
Yes. Which one specifically?
The first one, the trivial case.
This
Yeah.
guy.
So right. Yeah. So is in the second plot, is the probability for the scattering occurring 0 before the threshold energy is reached?
Mm-hmm.
But the scattering amplitude itself has a non-zero real component.
Yeah, so this is part of the cheat I'm giving you. This kinematic phase space factor here, rho, is identically 0 below this threshold. So it's killing this thing off. And the reason why we tend to plot rho m, besides the fact that it makes the amplitude proportional to unity, is that these cross sections here that are actually plotted here are proportional to rho m. There are more factors as well. This is why they're not normalized to unity, because there's other kinematic factors and constants that are involved. But this, why can't I go back? But this rho m is very common in cross sections. So that's why I plotted. But yeah, so while the amplitude itself has a non-zero part, this rho part kills it below threshold.
Right. Okay. Thank you.
Yeah. Yeah. My apologies for not explaining that, but good catch.
Thank you. Thank you.
Well, so we've been going for an hour and a half. Perhaps this is a good place to stop. Oh, I see one more question. Rahul?
Yeah, this isn't about today's lecture particularly. Is that fine? I want to ask it.
Sure.
Yeah, so we talked about color as a charge-like quantity. Does that mean that it's a quantity similar to charge in the way in which QED has a negative and a positive charge, and so we have 3 different charges, or is it some other kind of fundamental property like spin?
I mean, it works exactly like the electric charge, except now it comes in 3 versions instead of 2. And I would, yeah. So it's a property just like electric charge, the color charge is. Yeah. So your intuition is correct. Which I would categorize spin as being part of that fundamental nature of the fundamental particles, but it does work a little differently than those charges. So it's good to distinguish those 2, but it's still fundamental.
Okay, thank you.
You're welcome. I saw another hand raised, but then lower. So if you feel like asking, please. If not, then I think, oh, Philip.
Yeah, so color is an intrinsic property of the particle. It can't be acquired.
Correct. So the quarks have an intrinsic color charge. We don't observe color directly. because all of the hadrons that exist are colorless objects. So the color has to combine in such a way to make a color neutral object. But yeah, the fundamental constituents do have color. Aditya asks, why is a Lagrangian formalism preferred way to study QCD? So quantum field theories in general are generally studied with Lagrangians, because Lagrangians have understanding the symmetry properties of Lagrangian understanding the symmetry properties of a physical system is very easy with Lagrangians. It's harder to do that, say, with like Newtonian-like forces, which have issues in relativistic physics anyway, and quantum and relativistic quantum physics anyway. The Lagrangians carry over very nicely. And the Hamiltonian formalism also hides a little bit of the symmetries, even though it has some other useful properties itself. But it's very easy to convert between Hamiltonian and Lagrangian formalisms very easily because the Legendre transforms of each other. But in generally, just, you know, people study the Lagrange formalism because it's easy to formulate theories in terms of Lagrangians because we know their symmetry properties very easily. All right. So yeah, perhaps we should end here. And then this Thursday, we'll have opportunities for discussions, more detailed and whatnot. And yeah, join the Slack if you can, to ask questions there. If you have questions about the notebook itself, or you find errors in the notebook, please let me know. I wrote that notebook, so I'm interested if there's any issues with it. But please play around with it. There's no mandatory exercises. We want you to get comfortable with the idea of plotting complex functions and understanding their general features. I would say that's more important than trying to finish some exercise.
Maybe one thing so if you have any questions, like the ones that you were just asking, you should be able to access the Slack chat at this point. Some people said that although they were able to get in Slack, they're not able to see the Slack channel dedicated for the nuclear mentor program. I put the link for that inside the general chat for the Slack channel for Slack. So you should be able to see that link. So feel free to pass on these physics or math related questions there. Also on Thursday, since it won't be just this group, but there will be other mentees from other programs, the discussion is going to be largely more casual. It's going to be more about what you think about the program, how things are going for you, what you're learning about. Since there's so many of you, you know, not many of you, not most of you may not be asked to speak, but if there's a lot of shy people, perhaps I'll start picking people at random to give us a little report on what they've been doing. So if you want to take the opportunity to basically learn how to articulate the kinds of things that you've been learning about and what you're interested in, that's a perfect time to practice it. So I think
at what time will be this meeting?
The Thursday one would be at 12 p.m. Virginia time.
Okay.
So 1 hour before the Monday meetings. Okay. So I see there's a question about Lagrangians. Maybe let's move that to Slack to encourage the conversation to move there. So would you mind, Jonathan, moving your question to Slack and we'll have a discussion there? All right, with that, maybe let's say goodbye for now and we'll talk again later in the week.
Thank you.
Take care, everybody. Thanks, Andrew. Oh yeah, everybody thank Andrew. Clap emojis.
Thanks, Andrew.
I can't find the clap emoji, so I'm just gonna say thank you.
It's okay.